This is Step 1, 2011, Question 8. We're told the numbers m and n satisfy m cubed equals n cubed plus n squared plus 1. And the first part of the question tells us to show that m is greater than n. So, first thing to do is write out the m cubed equals n cubed plus n squared plus 1. And then note that how we can compare the left-hand side and right-hand side. So, we can say that the n squared term is always positive. So m cubed is always greater than or equal to n cubed plus 1, as n squared is always greater than or equal to 0. And that means that m cubed is always greater than n cubed. And now note with a cube function that it's a strictly increasing function, i.e. if m is greater than n, m cubed is greater than n cubed, and the equivalent relation holds. And so we can say that this implies that m is greater than n. And that's the argument done. Now, for the second part, we're asked to show also that m is less than n plus 1 if and only if 2n squared plus 3n is greater than 0. So let's start with one of these statements. Start with n plus 1 is greater than m. I've just written the inequality the other way around. And note that we've been working with cubing terms all this time, so let's cube both sides. So this is an equivalent sign, so it means that we don't need to, we can always go backwards in the argument. So here we've got n plus 1 cubed is greater than m cubed, and this is because cubing is a strictly increasing function. And n plus 1 cubed, if you expand it out, is n cubed plus 3n squared plus 3n plus 1, which is greater than m cubed. And remember that we have a equation star that represents m cubed. So if we replace m cubed with star, we get n cubed plus 3n squared plus 3n plus 1 is greater than n cubed plus n squared plus 1. And then subtracting n cubed plus n squared plus 1 from both sides will give us 2n squared plus 3n is greater than 0 as required. And note that this is an if and only if question. However, since each of these steps is directly reversible, we don't need to do the argument backwards because each of these signs shows that every single step can be traced back to the first line. So that's the end of that proof. We're now asked to deduce that m is between n and n plus 1 strictly unless n is between minus 3 over 2 and 0 included. So let's look at the line. So we've got m being between n and n plus 1 strictly implies that from the previous part, if m is less than n plus 1, as shown here, 2n squared plus 3n is greater than 0. And note that this is a quadratic, so we can look at it graphically. So factorizing it, we get n, 2n plus 3 is greater than 0. And drawing the graph, noting the roots minus 3 over 2 and 0, we see that this is greater than 0 when n is greater than 0 and when n is less than minus 3 over 2. So we can say that this holds for all n except for n between minus 3 over 2 and 0 included, as asked for in the question. Hence, for the last part of the question, we're asked to show that the only solutions of star for which m and n are integers are mn is 1 and minus 1 and 1 and 0. So let's looking at star again and bearing in mind what we learnt in the previous part of the question, we know that m is strictly between n and n plus 1 unless n is between minus 3 over 2 and 0. So we can split this up into two cases, the case where this holds and the case where this doesn't hold. So looking at case 1, where m is strictly between n and n plus 1, so n is less than minus 3 over 2 or n is greater than 0, i.e. not in this range. So if m is strictly between n and n plus 1, and n is an integer, n plus 1 is also an integer. So n and n plus 1 are consecutive integers, and with integers there cannot be another integer between two consecutive integers. So we can say that because there's no integer strictly between two consecutive integers, there are no solutions in this case. There is no integer value that m can take. So now we are forced to look into case 2 to try and find some solutions. So case 2 says that n is between these two values. So n must have an integer value, so it must be either minus 1 or 0. So let's look at both the cases at once. N is minus 1, so we get m cubed is 1. And this means that since we can just take the cube root of 1 as 1, we can say that m and n are 1 and minus 1 respectively. And now let's have a look at n is 0. So n is 0 means that m cubed is 1. Plugging it into star, that gives mn being the solution of 1 and 0 respectively, and this is exactly what we've been told in the question. So this part of the question is done. For the second part of the question, we are asked to find integer solutions to p cubed equals q cubed plus 2q squared minus 1. As with many step questions, we've been led through the first part, so now we're really thrown in the deep end with the second part. So the best thing to do is to follow the exact steps that we did in part I. So in part I, we first try to show that p is greater than q. So let's find m is greater than n. So in this case, let's try and find the range of values for which p is greater than q. So p is greater than q is directly equivalent to saying that p cubed is greater than q cubed. And this means that q cubed plus 2q squared minus 1, which is p cubed, as said here, is greater than q cubed. And then this gives us 2q squared minus 1 is greater than 0. And then rearranging this, we get q squared is greater than a half. And that tells us that q must be less than or equal to minus 1 over root 2, or q is greater than or equal to 1 over root 2, for p to be greater than q. So we can conclude that p is greater than q unless q is between minus 1 over root 2 and 1 over root 2. And now we want to do again what we did in part I, which was to prove, to find the range for which p is less than q plus 1. And that way we can bound p in a range. So p is less than q plus 1 directly implies that p cubed is less than q plus 1 cubed. Again, we've been using this theme throughout the question of cubing being a strictly increasing function. So if we do this and expand it out, we get p cubed is less than q cubed plus 3q squared plus 3q plus 1. We know what p cubed is in terms of q. So writing that out and then cancelling, we get q squared plus 3q plus 2 must be greater than 0. And then factorizing, you see that q plus 2, q plus 1 must be greater than 0. And then if we draw the graph of this quadratic, we can see where the range in which this right-hand side is greater than 0. It is when q is greater than minus 1 or less than minus 2. So remembering our aim, what we know now from before is that p is greater than q unless q is between minus 1 over root 2 and 1 over root 2. P is less than q plus 1 unless q is between minus 2 and minus 1. And note that these ranges don't overlap with each other. So p can't be less than q and greater than q plus 1. So it suffices to consider three cases. One where p is less than q, one where p is greater than q plus 1, and then one where p is between q and q plus 1. So let's look at the first case now. So that means that q is between minus 1 over root 2 and 1 over root 2, and there's only one integer value between those, because remember 1 over root 2 is greater than 1, so 1 over root 2 is less than 1. So the modulus of this is less than 1. So q must be 0, so p cubed is minus 1 if we sub it into here. That means that p is minus 1, and our solution is minus 1, 0 for p and q. And then the other case is that p is greater than q plus 1. So q is between minus 2 and minus 1, including both. So the only integers that work are q is minus 1 and q is minus 2. So trying both of those, q is minus 1, and subbing it into star, we get minus 1 plus 2, minus 1 is 0, and that gives p is 0. So our solution is 0, minus 1 for p and q respectively. And then q is minus 2 is the other case. So that gives us p cubed is minus 8 plus 8 minus 1. So that's looking back here, minus 8 plus 8 minus 1. And that gives us p is minus 1. So our solution is minus 1 and minus 2 for p and q respectively. And then our next range to consider is, our next case to consider is p strictly between q and q plus 1. But if you recall from the m and n situation, this has no integer solutions because there is no integer between two consecutive integers. And so it suffices to say that there's only three integer solutions, minus 1, 0, 0, minus 1, and minus 1, minus 2, to the equation p cubed equals q cubed plus 2q squared minus 1.